In the previous discussion, we were looking at how to determine if a closed-loop system is stable or not from frequency response diagrams. Now, for the ball plots, we said that we could identify two frequencies. One frequency is a one that where the magnitude plot crosses 0 dB. So it's the point on my diagram here. So if I look at the magnitude plot or the gain plot, 0 dB, go find where it intersects with the magnitude, and then you go down, you find that frequency. Okay, so you read the frequency from the x-axis, and then you go on from the phase plot. You find you go to the minus 180 degrees and come across until the line intersects with the phase angle line, and you go down there, you find the frequency. If the second frequency is higher than the first frequency, then the closed-loop system is stable. Now bear in mind, what we are trying to do here is to predict the stability of the closed-loop system from the frequency response plot of the open-loop transfer function. So in this case, it needs to be the transfer function of GS, which is your plot, and the transfer function of KS. So both needs to be in there. If it's not, then you have to find a way to add them together. The good thing is we can actually easily add the two both plots together. Now in this session, we're going to go one step further, and we're going to look at not only the stability, but also how stable they are. If they are stable, if indeed the first frequency is lower than the second frequency, the system is stable. But we want to see how stable they are. And we use some measures. Okay, one called gain margin, the other one called phase margin, to see how much more we can go before the system becomes unstable. Okay, so on this diagram, we need to make some definitions here. First of all, we need to define what a crossover frequency is. Crossover frequency is useful in the control design because it tells you broadly how fast or how slow a closed-loop system may respond to input. Okay, it's not exactly the same as the natural frequency or quantum frequency of the closed-loop system, but there's a link between the two. Okay, so the crossover frequency is often used in the control design. Now, the crossover frequency is basically my first frequency, where the magnitude plot crosses 0 dB. So it's this frequency there. So if you go to 0 dB, come across, and that's where my dotted line intersects with the blue line. Blue line is the magnitude plot. Okay, the dotted line is just what I added to, so I know where exactly it is. Go down there until you get to the frequency axis, read that frequency. This is your crossover frequency. Okay, then the phase margin is the phase angle. You need to look at the phase angle in the bow plot, which is the second plot here. Okay, you need to look at this at the crossover frequency. Read that value there. This is how much phase angle you have from the open loop transfer function. Okay, the distance between this point and minus 180 degrees is that indicated in the red line. This bit is your phase margin. Okay, so it's how far away it is from minus 180 degrees. That's your phase margin. Okay, so phase margin, the phase plot has to be above minus 180 degrees at this frequency for the system to have a phase margin. If it's below, then you have an unstable system, so you don't have any margins at all. Okay, so that's a phase margin. Gain margin is where you go to the second frequency. That's where the phase plot crosses minus 180 degrees. Okay. Now, when you get to the second frequency, you go up. You draw a vertical line there. You go up to check the magnitude plot. Now, this time, the magnitude needs to be below 0 dB. So magnitude will be a negative value. The distance or the length between the point here, the value at this frequency from your magnitude plot, and 0 dB, this distance is the gain margin. Okay? So gain margin, you read it from the second frequency. Phase margin, you read it from first frequency. First frequency is where the magnitude plot crosses 0 dB. And you go down, you find how far the phase angle at this frequency, how far it is from minus 180 degrees. Gain margin is you go to the frequency where the phase plot crosses minus 180 degrees. You go up, read to see how far the magnitude at this frequency is away from 0 dB. Okay, that will give you the gain margin. Okay, so three parameters here we need to pay particular attention to: the crossover frequency, the phase margin, and the gain margin. And of course, in some applications, for example, for a second order system, the phase plot never crosses 180 degrees. Then it's good news for you because the phase, if the phase plot does not cross the 0 dB, then your second frequency, omega 2, will be infinite. If the omega 2 is infinite, then your gain margin will also be infinite. So therefore, in the case like that, you don't need to worry about gain margins. Okay? So I'm going to give you a couple of examples here just to show you how to find these three parameters from open loop bulk plots. Okay? So over here, in this diagram, you have the bulk plots of the open loop plant. That's the GS itself. Okay, it does not include the KS. Now let's assume in the first instance, let's assume KS equals to 1. If KS equals to 1, then G times K equals to G, as I showed in the green block here. Okay. Now if K times G equals to G, then the bulk plot of G times K is the same as the bulk plot of G, which is what we have on the left-hand side. Okay, so I can use this because I know now this bulk plot is also the bulk plot of the GS. So in this, now we can actually go to 0 dB, come across. I added these lines there just to help me to identify the right values. Okay, so I'm gonna come across. This is where it intersects with my magnitude curve. Okay, so when it intersects with this, I go down, find the frequency. This is 10 to the power of 0, which is 1. So my omega C is 1, which is the corner frequency. So now I identify the first frequency, the crossover frequency. The second one is that I'm going to look at 180 degrees. I'm going to go over until I get here. This is where it crosses minus 180 degrees for the phase angle. And I go down. The frequency is 10 to the power of 1, so it's 10. Now, Crossover frequency is less than the second frequency, therefore system is stable. Now, when it's stable, I need to see how stable it is. Okay, so I need to find the phase margin and the gain margin. To find the phase margin, and then you go back to the crossover frequency. Okay, so you look up, you see how far the phase plot is away from minus 180 degrees. In this case, this is the phase angle is just below minus 180, maybe minus 95. Okay, and therefore the distance from that point there in the blue line to and the minus 180 degrees is 85. Therefore, your phase margin is 85 degrees. Okay, phase margin is represented by an angle. Okay, so that's 85 degrees. That's my second parameter, what I wanted to find, the phase margin. The third parameter, our final parameter I need to find, is the gain margin. Okay, gain margin, you go to omega 2. Omega 2 is where the phase angle equals to 180 degrees. So you go to omega 2, you go up until you see where the magnitude curve is. And see, it should be below 0 dB, but how far it is below 0 dB? So it's that little distance there. Okay? That is just below, I think this point there is just below minus 20 dB. So therefore, the distance between 0 dB and that point is 25 dB. So I have a gain margin of 25 dB. Okay, so crossover frequency, identify that. That's where the magnetic plot or magnetic curve crosses 0 dB. Omega 2 is where the phase angle plot or phase angle curve crosses minus 180 degrees. So that's my omega 2. Then the gain margin is where the phase margin is how far the phase plot is away from minus 180 degrees at omega c, at the crossover frequency. The gain margin is how far the magnitude plot at omega 2, how far away that is from 0 dB. So that will give you the gain margin. Okay, so it's different kind of technique or different kind of reading from what you use for the polar plot or Nyquist plot. You can actually read the gain margin and phase margin from the Nyquist plot or the polar plot as well, as I discussed before. Okay, but it's a lot clearer and easier to read the values out from the both plots. That's the case when Ks equal to 1. Now I'm going to actually change the Ks value. The point I'm trying to make here is that we need K times G. So if K changes, then both plots will be different, or the magnitude plot of the both plots is different. And K changes. Why K changes? Because we're trying to design controller. We don't know what a controller is. Okay, so in this case, if I change the K from 1 to 5, 5 is a real number. So real number has a phase angle of 0, so it does not affect the phase plot. But it affects magnitude plot. Because it's a 5, so I need to add this value onto the magnitude plot. But you can't add 5 to there directly. You need to work out the value in dB. So I'm going to do a 20 log 5. Okay, so I'm going to add 20 log 5 onto my graph for the magnitude plot. That moves the whole magnitude curve upwards by that much. Okay, so I actually sketched this line there in dotted blue. That is a new magnitude plot for G times K. Okay, blue line is for G. K is not 1, therefore I need to add that value there. Okay, now everything changes. If you look at the crossover frequency, so you go to 0 dB, you come across until this dotted blue line crosses 0 dB, which is this point. Okay. Now when that crosses 0 dB, you go down, you read the frequency. Now this frequency this time, this is 1. This is the first subdivision between 1 and 10. So this will be 2. This is 2, this is 3, this will be 4. So we have a crossover frequency of 4. Okay. Now the frequency where the phase plot across the minus 180 degrees is the same, because the phase plot is the same. So that would be still, if I go to 180, come across, and then this is where the phase angle crosses 180 degrees. If I go down, that's still 10 radians per second. Now system is still stable, because omega c is less than omega 2. But phase margin and gain margin will not be the same as in the previous case. This time, if I go to the crossover frequency, I go up to see, this is where the phase angle is. I want to see how far that is away from minus 180. So you can see there, it's just slightly more above 135, and so it's around, so it's a distance here is around 48. Okay, so now you have a phase margin of 48. The gain margin is also different, because my magnitude plot is moved up, so I will have less gain margin. Now, if I go to omega 2, the frequency, I go up to see how far away this dotted point line at this frequency. Now that is that much. And I said it's actually a lot less than 20 dB now. And it says 20 dB, but it's not, 25 it's not now. I'm going to change that. So that's now is power 15. Let me just. Just bear with me from there. Let me just get to here. It's about 15 dB, not 25, because this is 20. 20 is below here. 20 is there. Perhaps it's not even 15. It's about only 10. That's a little distance between 0 dB and where the dotted blue line crosses the green line. So it's not even that. I'm going to change that back as well. So it's only about 10 dB there. Okay, so the message here I can give you, is that first of all you need to consider G times K altogether when you use both plots. Now obviously if you are given the both plots of G times K, that's great, then you can actually use them direct. If not, you need to see how much Ks is, and then you add 20 log of that gain to the magnitude to the plot before you can start working on the crossover frequency, the phase margin, and then gain margin. Okay, so that's my example here. I have another example. Okay, now this is the both plot of G times K. Okay, I'm not making life difficult for you. I'm actually making life easier. This line you don't need to worry about Ks, because the both plot I'm giving you includes G and includes K as well. Okay. Now this time, if we're going to identify the crossover frequency, I'm going to go 0 dB. I'm going to go come across, that's where it crosses 0 dB, the magnitude. And I go down and read that frequency out. So if I'm going to read it, the scale is a bit fade, but so that's 1, that's 2, that's 3. So it's a bit slightly more than 3. So let's say 3.2, that's my omega C. If I want to find omega 2, I go to minus 180 degrees. And I go across, I can see that blue line doesn't really cross it. It stays on the top. Therefore, the omega 2, because it does not go over minus 180 degrees ever. Therefore, your omega 2 is infinite. When omega 2 is infinite, then we don't have a value for the gain margin. The gain margin will be infinite as well. Okay, so gain margin will be infinite. Phase margin is where, so for the phase margin, again, you need to go to the crossover frequency. That's omega C. So you go to that frequency, you check how far away the phase angle is from minus 180 degrees. It is that much. One division here, you can see this whole division is 45 degrees. This is a lot less than 45 degrees. Okay? It's actually less than half of it. Half of what 45 is 22.5. This is actually less than half. So let's say it's about 20 degrees. It's that distance. Okay, phase margin is distance. It is away from minus 180 degrees. So it's that measurement. Okay. I don't have an omega 2, or my omega 3 is infinite. Again, just emphasize because the gain margin therefore is infinite. So that's how you determine this. Okay, you determine the crossover frequency, you find omega 2, and then you can determine if a system is stable or not. If it is stable, then you can go to the crossover frequency, find the phase margin, and then you can also find the gain margin if your omega 2 is not infinite. If it's infinite, then it's simple. The gain margin will also be infinite. Okay, so we have gone one step further from from determining the stability. We are actually looking at how stable they are. Okay? And that's important because that next stage we can look at the design of a controller. We're not going to just use a controller simple gain. We're going to see how a dynamic controller can be added to the bulk plot of GS to give us what we want for particular design requirements. Okay? And then again, I got some examples for you of practical questions. Okay, so over here, what I'd like you to do is, this is the bulk plot of a GS. Okay, I'd like you to estimate the crossover frequency, gain margin, and phase margin when one k equals to 1, and the second case, when k is equals to 10. Okay, and to see if we can work some sensible values out. Thank you.